Welcome to a screencast on the hydrogen atom, taking a look at electron energy levels, transitions between energy levels, and the spectrum that arises from that, and what's known as the Bohr model of the hydrogen atom. Now, as we've seen previously, hydrogen, like other elements, has a unique emission spectrum that's created when hydrogen is energized and electrons and hydrogen atoms move up to higher energy levels than they normally reside in. They go down to lower energy levels and emit specific photons of specific energy, and that is what creates the spectrum of, in this case, hydrogen, but same idea for other elements as well. And for hydrogen, the visible spectrum has a red line at 656 nanometers, a blue-green kind of aqua-colored line at 486 nanometers, a purple line at 434 nanometers, and another purple line at 410 nanometers. Now that's the visible spectrum of hydrogen, and the spectrum of hydrogen also contains quite a number of lines that aren't visible to us but can be detected nonetheless, lines in the infrared and ultraviolet regions of the spectrum, and this is showing a somewhat expanded view of the hydrogen spectrum with more lines. Here are the visible ones, and then these are some that we can't see with our eyes but we can still measure. And in the late 1800s, discrete spectra were known. People didn't really understand why discrete spectra existed. It was a big source of confusion to the science community at the time. But nonetheless, there were scientists like Johann Balmer who were able to determine an empirical relationship between the wavelengths of the visible lines of the hydrogen spectrum and some integers. And Balmer was able to determine that if one of the integers was 2 and the other integer was 3 or 4 or 5 or 6, then this relationship held for the spectral lines, the wavelengths of the spectral lines of hydrogen. Then a little bit later, another scientist named Johannes Rydberg generalized this to include the non-visible spectral lines, and here the integers could be any integer, 1, 2, 3, 4, etc. And this relationship with r equals 1.097 times 10 to the 7th meters, it's a constant, sometimes called the Rydberg constant, and n1 and n2 being some integers, that relationship held for hydrogen. They didn't know why, but they nonetheless had established this relationship. Now, not only were discrete spectra, like what caused them, a big source of confusion or non-understanding of scientists in the late 1800s, in the early 1900s as well, after the electron was discovered, then it was still very unclear as to what was going on, because according to classical science, classical physics, an electron moving around a nucleus, so you could think of it as orbiting the nucleus, should continuously emit radiation, should lose energy, and should spiral into the nucleus, and atoms should annihilate themselves in a few split seconds. So this was called the death spiral of the electron, and it was not at all understood why that didn't happen. How could electrons even, or atoms even exist and have electrons orbit them? Well, along came a guy named Niels Bohr in the early 1900s and explained what was going on, especially in the case of hydrogen. And as a little bit of a recap, and here's the basic idea, it was proposed that there were discrete, specific, what are now called quantized energy levels for electrons in atoms, that electrons can only have certain specific energies. And the electrons can only be in certain specific, what are called quantized orbits. And again, this is a bit of a simplification, but it's a decent enough starting point. So we can have a first energy level, and electrons can be in that level or shell or orbit. We can have a second energy level, which electrons can be in, or a third energy level or shell or orbit, or a fourth, and so on. Now, if an electron is in a lower energy orbit and it absorbs some energy, it can go up to a higher energy level, and the absorbed energy has essentially moved the electron from a lower level to a higher level. Now, when the electron is in a higher energy, and this energy that moved it there has been used up, typically the electron won't stay in that higher energy level, but instead what it will do is it will go to a lower energy level and emit some energy. And it will emit energy in the form of a photon of light of very specific wavelength, frequency, color, or energy. And the photon that's given off, or the sum of the photons that are given off, is what we see as the emission spectrum of that element. Now, each transition for each element corresponds to a different amount of energy absorbed by the atom or by the electrons in the atom. So going from the first level to the third level absorbs a different amount of energy than the first to the second. And then same for the second to the third, or the second to the fourth, and it's different for each different element as well. So different transitions correspond to different energy photons. Now, for most elements, analysis of electron energy levels is way too complicated to do analytically. Turns out we can do that using some approximations and using high-powered computers to do very good analysis that's non-analytic, but that's approximate, but to very high degree of approximation. But that's higher-level quantum mechanics is what it's called. It's way beyond the level of this course, and so we're going to focus on what we can do, which is hydrogen. Hydrogen has only one electron, and it's relatively simple to do analytically. And it hinges upon the assumption or postulate or argument made by Niels Bohr, which was that these energy levels for electrons can be explained if we treat the electron as not just a particle, but as a wave. And if we say that each energy level has a discrete number of electron wavelengths, a specific number of electron wavelengths that fit in that orbit. So the orbit might have one electron wavelength that corresponds to its size of orbit, or 2 or 3 or 4, but you can't have partial electron or wavelengths to have the atom survive and the electron survive and not spiral into the nucleus. Now that's a little bit more technical than we need to get to. There's a kind of a long story involved with that. We're going to just cut to how we deal with this and what's our mathematical relationship. And here's how that goes. We have electrons in quantized energy levels, with the closest electron energy levels to the nucleus being lowest in energy, and as we go farther away from the nucleus, we have increasing energy. And for hydrogen, it's pretty simple, and we only have one electron. Now, if you get tired of drawing circles representing electron orbits, and it's also misleading because electrons don't really do little circular orbits, so what we often do is we go to what's called an energy level diagram, where the first orbit corresponds to the lowest energy, and we represent it by a line. Second orbit or shell or energy level, we also represent by a line, but higher in energy than the first level. Third energy level's higher yet. Fourth energy level's higher than that, and we keep on going. So n equals 1, n equals 2, n equals 3 corresponds to the energy level we're talking about. Now, here is roughly what this looks like, not exactly to scale. First energy level, second energy level, third, fourth, and then fifth, sixth, seventh, eighth, ninth, and they start packing closer and closer and closer together, and eventually we get to very huge numbers, like when n equals infinity, and we can't go any farther, so that's essentially the highest energy level for electrons in hydrogen. And it turns out that what Bohr did was established a relationship between the energy of a level, electron energy level, and its what we call principal quantum number. And so the relationship is E sub n, energy of the nth level, is equal to negative k over n squared, where k is a constant, 2.18 times 10 to the minus 18th joules. N is an integer, 1, 2, 3, 4, etc., for the first, second, third, fourth levels. And E sub n is the energy of a given level. So E sub 1 is the energy of the first level, E sub 2 is the energy of the second level, and so on. And n is known as the principal quantum number, or the main quantum number for a given element, and here we're dealing specifically with hydrogen. So this is a not to scale energy level diagram for hydrogen. In reality, the jump from n equals 1 to n equals 2 is actually even bigger, and the 2 and 3 and 4, etc. energy levels are even more squashed together than is being shown here. So it's spread out a little more just for space purposes. Now we can also calculate the value of the energy of each energy level for the electrons in hydrogen using this relationship, and so let's do that. E sub 1, the energy of the first level, is negative k, or negative 2.18 times 10 to the minus 18th joules, divided by, for the first level, n is 1, so divided by 1 squared. And then similarly, the energy of level 2 is that value k, negative of it, divided by 2 squared. Energy level 3 is the same k divided by 3 squared, and so on. And now, of course, we can complete the calculation, and the k value, negative 2.18 times 10 to the minus 18th joules, divided by 1 squared, is, of course, the same number. Dividing by 2 squared, or 4, gives us negative 5.45 times 10 to the minus 19th joules. Dividing by 9, 3 squared, gives us 2.42, negative 2.42 times 10 to the minus 19th joules. And then if we keep going, we can get E sub 4 and E sub 5. And then notice, eventually we get to huge values of n. And if n is infinity, well, infinity squared is really big. And negative k divided by a huge number, infinity squared, is 0. You divide by a monstrous number and you get 0. So our high energy is 0, and our lower and our other energies are below 0. This is just our relative scale. So negative 2.18 times 10 to the minus 18th joules for E sub 1, and so forth on up to 0 for E sub infinity. Now, what we can also do is pay attention to the transitions between electron energy levels. And when an electron is energized, a hydrogen atom electron is energized, goes to the second energy level, and then goes back down to the first, it emits and undergoes this electron transition from level 2 to level 1. It emits a photon when it makes that transition, but the photon of the 2 to that's created, if you will, by the 2 to 1 transition is of too high energy for us to see. But the photon created by the 3 to 2 transition is visible to us, and it's actually red. And the photons, so it produces photons of red light. The transition 4 to 2 produces photons of aqua blue-green light. The transitions 5 to 2 and 6 to 2 produce photons of purple light. And those are the 4 transitions that we can see. And the second purple light transition isn't shown here. It's running out of space to fit so many energy levels and electron shells. So the visible transitions are 3 to 2, 4 to 2, 5 to 2, and 6 to 2 for hydrogen. And they produce photons that are red, that are blue-green, and purple, respectively. Other transitions occur as well, but we can't see those. Now, let's also do a calculation of the energy, the frequency, and the wavelength for a photon produced by one of these transitions. So for this example, we're going to do the 3 to 2 energy level transition. And as mentioned already, that produces a photon of red light. So what's its energy? What's its frequency? What's its wavelength? And here's how we do the calculation. We know that the energy of the photon, or the photon itself, arises from the transition, and we're specifically talking about the 3 to 2 transition. So we're doing the change in energy, the difference in energy between the third energy level and the second energy level. That corresponds to the energy of the photon that's produced. Well, the 3 to 2 transition starts out at level 3, ends up at level 2, so this is final minus initial. And then, as seen previously, we were able to calculate the energy of these levels. Second level is negative 5.45 times 10 to the minus 19th joules. Third level is negative 2.42 times 10 to the minus 19th joules. Subtract the third from the second, and we get negative 3.03 times 10 to the minus 19th joules. Now notice that's a negative value because energy is given off. So the change in energy level, or difference in energy level when we start higher energy and go to lower, is going to be a negative value indicating that energy is given off. But now the energy is given off in the form of a photon, and the photon has an energy of positive 3.03 times 10 to the minus 19th joules. So we've now answered part 1 of this question. The energy of a photon produced by the 3 to 2 transition for hydrogen is 3.03 times 10 to the minus 19th joules. Now we'd also like to determine the frequency and wavelength, and notice we have some equations, some relationships that help us here. Energy of a photon is equal to Planck's constant times frequency. So we can solve for frequency equaling energy of photon divided by Planck's constant. And we just figured out that the energy of the photon was 3.03 times 10 to the minus 19th joules. Planck's constant, 6.626 times 10 to the minus 34th joules seconds. And the joules will cancel. And it gives us 5.47 times 10 to the 14th per second for the frequency, which is of course the same as 5.47 times 10 to the 14th hertz. So we now have the frequency. And last but not least, let's do the wavelength. And we have a relationship between wavelength and frequency. We just figured out frequency, so we can solve for wavelength. Wavelength is equal to speed of light over frequency. Speed of light, 2.998 times 10 to the 8th meters per second. Frequency, we just figured out, 5.47 times 10 to the 14th per second. Per seconds cancel, giving us 6.56 times 10 to the minus 7th meters for the wavelength of these photons of light. And we often do our wavelengths in nanometers, so this is 656 nanometers. And either of these answers are fine, but it's very common to express our wavelengths for hydrogen in nanometers. Now let's relate this to the observed spectrum of hydrogen, kind of overlaid here over a continuous spectrum of visible light. So you can see we're able to see light of wavelength from a little under 400 nanometers to just about 800 nanometers. The short wavelength end of the visible spectrum is purple colored light, and then it goes through at the high wavelength or low energy end, red light at about in the 700 or 800 nanometer region. And the 4 spectral lines that we're able to see for hydrogen are at 656 nanometers, the one we just calculated, which is the 3 to 2 transition. The 4 to 2 transition is 484 nanometers. The 5 to 2 transition is 434, and the 6 to 2 transition is 410 nanometers. And those calculations are ones you might want to do or might even be asked to do. And then this shows the more complete transition possibilities for hydrogen. The ones we can see correspond to transitions to the second energy level, so 6 to 2, 5 to 2, 4 to 2, and 3 to 2. But there's also transitions to the first energy level, there's transitions to the third energy level, and those exist. They create photons. We just aren't able to see them with our naked eyes. And then, of course, remember that Electrons move to higher energy levels when light or electromagnetic radiation is absorbed, and they go to lower energy levels and emit light when they do that. And that is it for the hydrogen atom in the various aspects we are going to look at.